All right, gang, here we go. So this is Physics Unit 4, Part 2. We're talking about Newton's universal law of gravitation. All right, so let's start off thinking about gravity here for a second. So if you have an object that's on a spring scale, so a spring scale, is like what you put your, we've used them in class a couple of times, but so it's like what you put your fruit on at the grocery store or for vegetables, like you're up there, and then you got some sort of spring up here, and it uses how hard the spring pulls and all that stuff to measure how heavy your fruit is, so they know how much you need to pay them. Anyway, so what's the source of the force that's pulling down on your object against the spring? Well, we know that this force is gravity. So think to yourself, could you diminish this force in some way? Um, yeah, you could diminish the force that's pulling down by either removing some of your fruit or, and we'll show you in a little bit here how if you manage to get your spring scale farther and farther away from Earth, then you'd have less force pulling down. Okay, if you had your object in a vacuum, so think about that for a second. So if you put them in a vacuum, meaning there's no air moving around or in or on your object, would that change anything? The answer is no. It would still be pulling down. And then what if the Earth stopped rotating? All right. Well, if the Earth stopped rotating, you'd have bigger problems than whether or not you're paying for all of the fruit you should be paying for. But number two, no, the force would still be exactly the same. Okay, and so we're going to talk about gravity here and Newton's ideas. So Newton started off with this thought experiment. He said, well, what if you took a cannon and you launched it and you at faster and faster speeds, right? And he knew that the Earth was curved, right? And so here's his idea. Like you shoot it, it goes this far and then this far. And eventually, if you shot it fast enough, the rate at which it's falling, its y-axis is changing, it will be equal to the rate at which the surface curves, right? And so as you're falling, you're just continually falling, right? Because you're going forward. But as you fall, you're missing the Earth over and over again. And so that was his idea of how he reasoned that the reason the moon stays up in the sky the way it does is because it's just moving fast enough and far enough away that it's just continuously moving or continuously missing the Earth as it falls, and then us, the sun, and so on and so forth. And so he came up with this formula here that you need to be familiar with. It's called Newton's Law of Universal Gravitation. So the force of gravity, or the gravitational force, is equal to G, capital G, and that's a constant value. We'll talk about how that gravity value, or that constant G, came from, times the mass of the two objects divided by the distance between them squared, the radius of the distance between them squared. All right. So you can see that as these masses increase, your force of gravity will increase, and as this radius decreases, your force of gravity will increase. So it's proportional to the masses and inversely proportional to the distance, or the radius squared. All right, and this value here is your value for g. Okay, and it has the units it does, so that all of these values here, your two masses, and your radius will get into newtons when you multiply and divide them in just the right way. And so it's 6.673 times 10 to the minus 11th. Notice that it's 10 to the minus 11th. That's a really small number, so that's going to take in. So take note of that. That's going to be an important thing here in a second. And so really what we're talking about here, force of gravity, is this idea that these forces that they are, so this is the Earth and the Moon, that these forces of the Earth on the Moon and the Moon on the Earth, and vice versa, it's just, what is that force? How hard are they pulling on one another? And remember this notation that we've used in the past: the force of the moon on the Earth versus the force of the Earth on the moon. That's how you read that there. And they're both equal to force C. So that's the centripetal force. Remember that, because the centripetal force always points towards the center. Okay. So anyway, so there's this guy named Cavendish who decided to take it on himself to find the value of g. And so he came up with this experiment. And if you Google YouTube, find Cavendish setup experiments and stuff, you'll see lots of people have tried to do this, set up this experiment, and it works. However, it's really, really, really finicky. Okay, it's hard to get it to work exactly right. And so this is like one of the big things that like flat earthers point towards, like, oh, gravity's a lie, it's not real, and like this Cavendish experiment doesn't actually work, like blah blah blah. So anyway, so if you're ever looking for a good time reading some intense people's ideas, then you can. Miles, I'm busy right now. Shh. I know. And so you can look up Cavendish experiments. All right. So anyway, so he set up this experiment here where he took this guy here that was floating, okay, on a string, and he measured and he let it sit until it was completely still, and then shined a light source off a mirror. So that's attached to the string. This doesn't really show it very well. This guy's attached to the string here, and so this light bounces off the mirror, and he can measure how far it is here. And then he introduces two masses, one on either side, and because of gravity, this force, then this ball gets dragged this way, and this end gets dragged towards this ball here, and you end up moving your torsional string, and so this light moves from this spot on your meter stick to this spot on your meter stick, and you get this change in your distance. All right, and so you get this movement here. All right, and so that was kind of like what his idea was here. So he used this distance here as his radius between the masses and the balls, and then he used the distance that traveled here. He found that degree changed, and he plugged it all into Newton's law of gravitation, and he found G. All right, and so and that's kind of the basic idea of it. It's really hard to set up, otherwise we do it in class, but it literally is like, based on, I watched like half an hour of videos of watching people try to do it, and I have no desire to do it myself now. Anyway, so he found G, so we can thank Cavendish, and lots of other physicists have proved it. So flat earthers think it's a hoax, but it's pretty funny to read their comments. So anyway, so gravity is universal and exists between all masses. Why isn't this force easily observed in everyday life? Okay, so like if I'm standing next to a really big building, why do I not feel, I obviously feel the earth pulling down on me, why do I not feel like that building is pulling me towards the earth? And the whole idea is that this value for G is so dang small that compared to that, as long as my mass compared to the building is or as long, if the difference in the masses aren't big enough, then the force of that gravity is going to be negligible. You just won't even feel it. But because the my mass compared to the Earth is so big, then I do feel that pull by the Earth. And so it's really, gravity is kind of an interesting idea, because it really starts to only take effect, and you can feel it when these objects are like stupendously large. Okay. So a good example of this is ocean tides, and there's, so what causes the tides? How often do they occur? Why do they occur at certain times? And are they at the same time each day? Okay, and the idea is that ocean tides are caused by the Newton's law of gravitation. Okay, so if you think about the moon above the Earth, right? So there's the moon, and then there's the Earth. Okay, the Earth has water on it. I know that's surprising, right? So you got water on the Earth, right? Okay, and so when the moon's above the water, remember, universal law of gravitation is talking about the distance between the centers of these two objects. Okay, but the water is on the surface of the Earth. So this water that's closest to the moon gets dragged, it feels a harder pull of gravity by the moon than the water that's on the other side of the Earth, right? Or the Earth in the middle. And so what really happens is this water gets kind of dragged closer to the moon, because it literally is closer to the moon, so it feels more gravity. All right. And so it accelerates more rapidly towards the moon than the rest of the Earth does. So you get kind of this bulge as the water moves towards the moon. And then this part of the Earth here is also moving more rapidly towards the moon, right, than the water on this side, right? And so this water here suddenly becomes more shallow, and so you get this like oblong shape-ish kind of thing going on, where the water on this side of the Earth gets dragged towards the moon, and the water on this side of the Earth doesn't feel as much of a pull as the rest of the Earth, so it kind of gets flattened out a little bit. And so as the moon circles and orbits the Earth, it goes around in a circle here, then different parts of the Earth experience these two different forces, either being pulled towards the Earth or not being pulled as hard towards the moon. And so anyway, so that's kind of where the tides come from. And then calculating the value of G. All right, so this is our main formula. We'll do a little mini lab in class where we kind of calculate this value of G. And so you take the force of gravity, All right, and so you can find the force of gravity just by taking the mass, right? Mass times or taking the mass on a scale and divide it by the mass itself, and you get the value for g. And so this formula here is really the kicker here. And this part also plays an effect as well, the gravitational constant times the mass of the Earth over the distance between the two squared. So here we go. So we're going to do a couple of practice problems here. It says find the gravitational force that the Earth exerts on the moon when the distance between them is 3.84 times 10 to the 8th. And so we know that Fg, we just learned this formula, is equal to g times mass of the Earth times the mass of the moon over the distance between the two of them squared. And so the g is 6.673 times 10 to the minus 11th, right? And the mass of the Earth is 5.97 times 10 to the 24th. And the mass of the moon is 7.35 times 10 to the 22nd. And then the distance between them is 3.84 times 10 to the 8th. And then we're going to square that sucker. All right. And so we get 6.673. Now remember to use your parentheses wisely when you're doing this whole thing here. Otherwise, you're going to get bad numbers, and then you'll feel really silly. So 5.97 times 10 to the 24th. Times 7.35 times 10 to the 22nd. We're going to divide all of that by 3.84 times 10 to the 8th. And then we're going to square it. We get 2.97 times 10 to the 30th. What did I do wrong? Did I forget something? Here we go. Problem solving. G m1 m2 over r squared. No, I didn't. I must have put something in my calculator wrong. Unless I got the wrong g. 6.673 times 10 to the minus 11th. Nope, 6.673 times 10 to the minus 11th. That's right, 5.9. Oh, I forgot to multiply it by g. Whoops. Times 6.673 times 10 to the minus 11th. There we go, and we get the right answer. You know, see, this is what I'm talking about. Running your calculator right is important. 1.99 times 10 to the 20th. All right. One more practice problem. We're going to find the strength of the gravitational field at a point that's 3.84 times 10 to the 8th meters from the center of the Earth. And so that's the formula we just used right here, Fg over m, or gme over r squared. All right. So gme over r squared. Gme over r squared. So g equals gme over r squared, right? So g is the 6.673 times 10 to the minus 11th over the mass of the Earth, which is 5.97 times 10 to the 24th. I should have given myself a little bit more room. Over r squared, and that r here is that 3.84 times 10 to the 8th. And we're going to square it. All right, so plug that all into our calculator and just make sure we get the right answer. 6.673 times 10 to the minus 11th times 5.97 times 10 to the 24th. I'm trying to make sure I don't screw it up again. 3.84 times 10 to the 8th, quantity squared. And we get 0.00270. 0.00270. And the force, since it's gravity, it's an acceleration. So it'd be meters per second squared, or Newton meters. All right? Or newtons over meters, sorry. And so anyway, so that's it for part 2. Next part here, we'll talk about Kepler's laws. It's pretty fun. Talk about the motion of planets and so on and so forth. Anyway, do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.